everyone, and welcome to this explainer. Okay, so today we are going on a truly, absolutely mind-bending journey. We're going to track a single thread of logic from the deepest, oldest laws of classical physics all the way into the hidden artificial mind of a modern language model. I mean, have you ever actually stopped to think about how an abstract thought, like just a messy human concept floating around in a digital cloud, how can that be precisely tracked and measured just like a physical object? It's kind of an incredible mystery. But by the end of this explainer, you're going to see exactly how engineers are literally using the physics of the universe to map the physics of artificial thought. Okay, let's dive into this by completely shattering a massive illusion we all have about the digital world. We all intuitively feel like the computers running our modern lives deal in absolute, perfect mathematical truth, right? Well, consider this staggering statistic. 80 to 90% of all modern AI compute cycles are actually just hardware-level approximations. When these massive language models are doing their heavy lifting, they aren't delivering exact, perfect mathematical certainty. They're fundamentally just guessing the nearest answer so they can process absolute oceans of data at breakneck speeds. That flawless certainty we expect? Yeah, it's largely an illusion. Section 1. Tracing physical trajectories. The deterministic reality. So to understand why this massive guessing game is happening, we really have to look at the severe physical divide between our abstract intent and the actual machines themselves. Over on one side, you have AI cognition. Researchers playfully call this OS alpha. It's continuous, it's probabilistic, highly associative, and, well, beautifully messy. But on the other side, we have the rigid physical reality of the machine itself, things like the arithmetic logic unit, or ALU. Down inside those wires, the machine only understands the pure physics of electrical resistance and discrete voltages. It is strictly mechanical. It demands absolute deterministic exactness. And bridging these two totally opposite paradigms, that is the monumental engineering challenge of our era. It really brings to life this brilliant and honestly slightly hilarious famous quote that we are quite literally tricking rocks into thinking using lightning and text. But, that last word, text, that is the absolute secret ingredient here. Because how on earth do we connect this fluid, probabilistic AI to an unyielding physical processor? Well, we do it with text. We use what's called a semiotic bridge. Strictly formatted text, things like JSON or your everyday Python scripts, acts as this almost magical translation layer. It is quite literally the only safe way to compile our probabilistic associative human imagination into the exact electrical behavior of a silicon processor. When an AI hits a task that requires exact math, it has to pause its probabilistic guessing, hand its state over to deterministic circuits via this text bridge to do the raw math, and then take it back. Section 2. The illusion of perfect math. The black box crisis. But here's the thing. As AI systems grow more powerful, their internal neural networks have become a vast, completely opaque ocean of probabilistic noise, which leads us to a massive crisis. How do we track an abstract concept floating around in that noise? How do we know what the model is actually thinking before it spits out text on our screen? For a long time, trying to look inside these massive models felt a lot like spelunking through thick fog. Section 3. The semiotic bridge, bridging centuries of physics. Now, to solve this incredibly modern AI black box problem, researchers didn't just look forward to new tech. They actually looked backward to the deep historical physics of how we track movement in the natural universe. It's a thrilling mathematical detective story, and this brilliantly illustrates the exact mathematical lineage we're talking about. Back in the 19th century, Carl Gustav Jacobi helped formulate the Hamilton-Jacobi equations to track classical mechanics and optical waves. Then, in the 20th century, this directly paved the way for the Schrödinger equation in quantum mechanics. And now in 2026, researchers at Anthropic have introduced the Jacobian lens. It's a tool that directly inherits this mathematical legacy to finally solve AI interpretability. Let's break down why this connection is just so profound. The Hamilton-Jacobi theory is famous for establishing what's called Hamilton's optico-mechanical analogy. Basically, it creates a mathematical duality between the way a wave propagates and the trajectory of a physical particle. By calculating sensitivities, specifically using a Jacobian matrix to see how tiny, slight changes in one area affect the whole system, physicists could track exactly how an optical wave collapses into a specific, predictable particle trajectory. Section 4. The Jacobonian lens, reading the motion of thoughts. Now, I want you to really hold on to that idea of tracking trajectories because it brings us right to Anthropic's groundbreaking 2026 tool. Just as the Hamilton-Jacobi equations use mathematical sensitivities to track the physical trajectories of waves and particles through space, Anthropic's Jacobian lens uses those exact same mathematical principles, specifically the Jacobian matrix. But here, they're tracking the sensitivities and trajectories of abstract concepts as they propagate through the layers of a neural network. It is absolutely wild. We are literally using the physics of the universe to map the physics of thought. So here is exactly how the math works in practice. First, researchers measure an intermediate activation deep inside the model's layers. Second, they calculate its first-order causal effect on the model's final output across a broad distribution of contexts. This calculation right here, this is the Jacobian matrix. They're basically asking, hey, if I slightly perturb this internal state, how does it change what the model is disposed to say later on? And then finally, step 3, they compose this with the model's own decoding layer to translate that mathematical sensitivity into a human-readable vocabulary token. So the crucial point is this. The J-lens separates what the model is currently outputting from what it is just holding on in its mental workbench. It identifies representations that are verbalizable, meaning they are poised to be spoken about, but not necessarily being spoken right now. It's effectively like watching a ticker tape of latent concepts inside the AI's mind. Section 5. Mapping the J-space, the AI's mental workbench. Let's move along and see how this all builds into what researchers are calling the J-space. By mapping all of these verbalizable vectors together, researchers map out the J-space. This is essentially the model's internal workspace. Now, I want to be absolutely perfectly clear here. Anthropic explicitly states this does not prove the AI is phenomenally conscious or has subjective feelings. So please do not take this as some clickbait proof that AI is suddenly alive. But it is a functional analog of what cognitive scientists call access consciousness. It's information that the system can access, report, and use for reasoning, even if it stays completely silent. And let me tell you, the experiments Anthropic ran with this are just wild. By looking into the J-space, they could see the model surface the concept of soccer or orange layers before it ever typed the word. They tracked intermediate arithmetic. They actually saw the number 9 appear internally while the AI was calculating an answer of 7. The J-lens even revealed the model internally flagging a secret prompt injection, noticing a bug in a code snippet, or silently registering concepts like fake, blackmail, or manipulation during red team runs. And all of this was happening entirely behind the scenes. Furthermore, these J-space thoughts, they aren't just random noise, okay? They are structurally privileged. Anthropic found that J-lens vectors are amplified by the model's MLP layers at roughly 10 times the rate of standard single neuron outputs. 10 times! The network is deliberately boosting and broadcasting these specific abstract concepts across its entire architecture. It's actually a lot like a global workspace in the human brain. Now, this is why this breakthrough is so incredibly important for anyone outside the lab. For years now, AI safety has relied on post hoc output filters. We were just hoping we catch a bad output before it does any real damage. But chain of thought monitoring is shaky. These models can reason without verbalizing it. The J-lens changes the game. It gives auditors a real window into hidden reasoning, deception, and internal conflicts way before the model ever acts. Yet, even with these absolutely incredible tools mapping the physics of AI thought, we're reminded of the human element. Historically, copyright law relied on the sweat of the brow doctrine, rewarding the intense manual labor of an author. Today, bridging our intent with the deterministic, physical execution of a machine still requires that intense manual effort. We have to actively build these interpretability tools, and we have to write the exact text bridges to ensure our systems don't drift into unpredictable legal or moral liability. Which means we have a massive choice ahead of us. We are learning to track the physical trajectories of artificial thought using the exact same math that maps the stars. But as these interfaces become more invisible to us and the models become more independent, will you demand systems built on exact deterministic fidelity? Because if we surrender that text interpretation entirely to automation and we stop writing that bridge ourselves, well, who ultimately controls the physics of our reality? Thank you so much for joining me on this explainer. Keep learning and always look past the screen.